course, for organizing and also inviting me and also my colleague, Yuri. So I need to say that this is a joint work with my PhD supervisors, all of them, I guess, Gareth, Pavel, and Mario. So I'll be talking about, as Bruno said, about ways to make Monte Carlo a bit more efficient for the calculation of something very specific, which I'm calling the risk allocation problem, which I will define now. So the risk allocation, for those who do not know, is the process of distributing the portfolio overall risk into its different constituents. So you may think that we have the var, let's say that the var of a portfolio is X, and a portfolio with D assets, and we want to know how much of this X is due to the ith asset. So in our notation, I'll say that the P&L of the portfolio is called S, and it can be decomposed like this. So S is equal to the sum of the D components of the portfolio. So the components will be called Z. So there will be two examples that I'll have in mind, and you can have in mind as well for this presentation, which are, the first one is an operational risk problem. So Zi is the annual operational loss in the ith line of business. And the other problem that I've been working for a while now is an insurance, an actuarial problem, where Z is the annual claims payment due to a specific line of business. So I'll say a few words at the end if I have time about this kind of risk, which are the new risk, old risk, large risk, and et cetera, et cetera. So in both cases, I will assume that the risk of the portfolio is being measured as a function rho, and this function rho will be the expected shortfall of the portfolio in this case. So expected shortfall or conditional value at risk. So for me here, all the Zi guys here will be positive random variables. So that's the definition of the expected shortfall in this case. Okay, so one possible strategy to decompose the risk of a portfolio, like I said, is to compute the risk measure for each specific risk. So the problem of doing this is that we'll have this kind of problem. So we may have that the total risk of the portfolio is not exactly equal to the sum of the marginal risks. So this will not be exactly the same thing. And of course, we'll be ignoring any kind of diversification benefit in a portfolio. So this is not exactly a good idea to do, I think. So one of the most popular ways to do this kind of risk allocation is to follow what is called the Euler allocation principle, or allocation by the gradient, which is to calculate the risk allocation for the ith unity of your portfolio as something like this, which is an expected value of the ith loss, let's say, conditional to the fact that the total loss or the total P&L is larger than the var. So for me, this alpha here will be a quantity that's very large. So this something like 0.99 or 0.999, So this is the probability, the expected value of the marginal loss conditional that the joint loss is being large. So one of the immediate properties of this kind of Euler allocation is the fact that it's summable, right? So you can sum the marginal risks, and it will be exactly the risk of the portfolio. So that's a good property. So one of the drawbacks, and that's the drawback that leads to this work, is the fact that this guy here may not be available in closed form, and then here comes the Monte Carlo. Okay, so in simple models, like if you say that all the joint risks are Gaussian distributed, you have that this kind of guys here can be calculated in closed form. I think Ulf will talk about Gaussian mixture, right? So I think you can also calculate for Gaussian mixtures this kind of quantities here is in closed form. So just a bit more notation. There will be a lot of indexes. Sorry, I'll try to make them clear. So I'll say that B is the var at some level, let's say 99%. And bold letters here for me will be the vector of random variables or observations for these random variables, the d-dimensional guys. So our aim by the end of the day is to sample from this distribution, given that we are trying to do some Monte Carlo approximations. It will be sample from this pi distribution, which is defined as something like this. So let's say that gamma is the unnormalized version of pi. So the normalizing constant here is just the probability that the sum of z's, so the s, is larger than b. So this is something that we know exactly. So this guy here, if this is 99, this is 0.99. Or, sorry, 1%, 0.01. And so gamma is the unnormalized version of pi. That's something to remember. I'll use it a lot of times. So directly sampling from this conditional distribution, so the conditional distribution of the vector z, given the fact that the sum of the components of z is greater than something, I mean, sampling z and then only accepting the samples that satisfy this condition will be very inefficient, right? Because we'll be wasting 99% of the samples on average due to the fact that they will not satisfy this condition here. So one obvious alternative from doing this kind of naive sampling procedure is to try to do some importance sampling. So importance sampling in a nutshell, to generate samples from that guy there, that pi, which is the conditional density, we can sample from an auxiliary distribution Q. We should calculate the unnormalized weight, which is the ratio between pi and Q, or gamma and Q for this matter, and then normalize this weight by the sum of the weights. Okay, so this is very simple procedure, and then this set here of samples from Z with weights capital W is a weighted sample from this distribution pi. So given a weighted sample, what you can do is to approximate an expectation of any test function phi as something like this. So it's a weighted average of the functional applied to the sample applied to the jth sample. So this is very simple, but it will help to understand some of the algorithms I will present. So the only problem here, and that's where the difficulty is that it's very hard to, in general, it's very hard to construct a good importance density Q. Okay? So what is the idea here? The idea is to use what is called the sequential Monte Carlo. So instead of trying to design an importance distribution that directly targets the conditional distribution that we are aiming at, what we can do is to split the problem into simpler steps, something like this. So we can construct a sequence of intermediate distribution bridging the unconditional distribution, the pi or the phi without any conditioning here, and the conditional distribution we are interested in. So given a nested set of bounds, let's say that B0 is minus infinity or 0 if our random variable is positive, we should set some B1 up to BT, where BT is capital B, and capital B is the value at risk we are interested in. And we construct a sequence of probability densities pi t, where each pi t is proportional to gamma, and each gamma is conditional on the sum being larger than the BT. Okay? So now we have a sequence of simpler problems, let's say. And so this is also important for some things I will say later, that this sequence of levels, which are exactly some value at risks, they can be calculated on the fly. I'll come back to this later in the end. So let's just say a few words about sequential Monte Carlo in general. So let's say that we have a sequence of distributions pi tilde. And for me, differently from Yuri, I'll say that these distributions are defined on the path space in the sense that the support of each pi tilde is a space ET. And each one of the ETs is larger in dimension from the previous ET. So if you think in our examples, ET will be something like RD to the power T. So this will be defined on the set of paths. So our Z has dimension T. Sorry, our Z has dimension D. And for each time, we'll be appending new Z. So this distribution will be defined on the space RD times RD times RD. So as we did before, we may assume that pi tilde T is known up to a normalizing constant, which is still called calligraphic Z. And Z1 to T will be defined as the collection of random variables or values from Z1 to ZT. Different from Yuri, I'm not using capital letters for paths. So the approximation for Z tilde will be given by a weighted sum of random variables, exactly as we did for importance sampling. Here in this context, all the samples will be called particles, and that's why you have also the name of particle filter and this kind of things. And so exactly as we had before, if the path Z1 to T sample, the ith sample for this path and the weight WT for the ith sample forms a weighted sample for pi t tilde, we can approximate expectations of any function of these guys. Okay? All this is to say that everything works the same way as it worked as for importance sampling, with one more index. Okay, so the algorithm is very simple. In the first step, you need to start with a simple importance density. Let's call this Q1. Remember that this Q1 is targeting now something that's much simpler than the constrained distribution. So Q1 is targeting a distribution that's unconstrained. So this is easy to design. You can even sample, if you are able to, you can sample from the correct distribution, unconditional to anything. And you calculate the weights. They can be 1 over n if you're sampling from the correct distribution. So this step here is easy. So for t equals to from 2 to capital T, we define the importance distribution on the path space as the importance distribution at the very beginning, multiplied by a sequence of Markov kernels that I'm calling Kj. So these Markov kernels have the effect of they take your sample at the time t minus 1 and take it forward on time, and this is algorithmic time, to time j, so from j minus 1 to time j. So we take the product of all these densities here. So we define this as an importance density. To sample from this guy here, we only need to sample from capital T, k at time t, fixed all the points at t minus 1. We just sample from this distribution here. And then we calculate our importance weights like this. So the important weights at time t, they will be proportional to the importance weights at time t minus 1, multiplied by the ratio of gammas and k. Okay, so you just do the math dividing this guy here by the target distribution defined on the path space. Okay, so then you normalize the weights, and then you have a simple weighted sample from your distribution pi. Remember that the distribution pi tilde is something that's defined on the path space. So from Z1 to ZT. So this is a simple algorithm. This gets complicated if you try to do this. On top of doing all the steps I told you before, we can include a step that's called the resampling step, where we try to avoid the fact that some of the weights may be very large. So some of these weights may be very close to 1, and all the weights, of course, will be very close to 0. So we can resample proportional to the weight somehow, and this induces some interaction between the samples. And so this starts to get the algorithm a bit more complicated to analyze, but it's still very simple to implement. So to avoid this kind of problems of having, but this induces a different problem, which is the sample impoverishment, where you have a lot of samples at the same point, all of them with weights 1 over n, but they are at the same point. So what we can do is to apply a Markov kernel again, which leaves this distribution invariant. So we start with a sample that was z, we resample, we get something that's z bar, and then we apply a Markov kernel to this sample, and then you get a z bar bar. So the notation is terrible. There are lots of indexes, but I hope it's not that hard to understand. At least it's not that hard to implement if you want to try. Okay, so this is a problem on the path space. But now let's imagine that we have a sequence of probabilities, as we have, that's defined on the same support. So let's say that this is pi t without the tilde. So the tilde was for the path space. And defined exactly as before. Z is the normalizing constant. Gamma is the unnormalized version. And the idea of the SMC sampler, which was introduced by Pierre Del Moral, Arno Doucet, and A.J. Jarzler in 2006, the idea is to construct from this sequence of distribution to construct a sequence of distributions on the path space. Okay, so the way to construct the sequence of distribution on the path space is to start with the distribution you want and multiply it by a conditional density. If you choose this conditional density to be as something like this, the product of many Markov kernels that work backwards on time, it's very simple to, so first of all, it's very simple to see that this guy here, Z tilde, gamma tilde, will have a marginal equals to this guy here, which is the one we want. So if we have a weighted sample for this guy here, we also have a weighted sample for this guy. Okay, so if you have a weighted sample for for the distribution defined on the path space, you can go back to the slide where I said you can apply any functional, and then you can apply a function that's defined only on the last time. So a weighted sample for this guy here on the path space solves the problem for a sample for this guy here on the marginal space, let's say. Okay, so the algorithm is very simple, it's exactly as before, but taking the ratio of Q1 tilde and Q2, sorry. We take the ratio of these guys here, this one, and, sorry, I did not put it here. And the importance distribution is also the same thing. So if I go back here, the importance distribution I defined here is exactly the same as I'll use now, because now I'm on the path space, so I can do exactly the same thing as I did here. So I go back, forward, sorry. I can define the same importance distribution for the denominator, and for the numerator, I use this guy here. So it's just taking the ratio of this distribution here with this distribution here. Okay, so this will give us importance weights for these guys on the path space. So if you work out what are the importance weights, it looks like this. It now depends on these backward kernels that we define now, the forward kernels, and the distributions we are targeting. Okay, so we can also include some resampling and this Markov kernel for the diversification. Okay, so let's now talk about something slightly different. I promised the last extension I'll talk about this kind of things. So let's remind ourselves that S is the sum of Z, B is the value at risk, and we want to estimate this guy here. So even if our model is defined through a parametric form, what we are interested in calculating is something that's not dependent on the parameter, right? So I want to do inference based on this distribution here, which is a distribution. So you can think of this guy as a likelihood, the way you define your model. So you can say that Z conditional on some parameters theta is multivariate Gaussian or T or a crazy copula with some even crazier marginals, but you need to integrate out the parameter uncertainty. And so the way to do it, so you create this distribution here, which is a kind of predictive distribution where you integrate out with respect to the distribution of the parameter. So now I'm being Bayesian with this guy here without saying the word. So I can say that this guy here may act like a prior, but in our case it will act like a posterior. So if you want to think of this as a Bayes theorem actualization, you may think that this is already a posterior, this is still the likelihood, and this is the distribution we want, which is a predictive distribution because it's given the data. Okay? So now if we have samples from this guy here, we are in trouble. If we don't know the posterior distribution in closed form, and we don't know how to solve this integral, we don't know this guy here in closed form. Okay? And then it's a problem. Because usually we will have samples from the posterior distribution, and then we'll solve this integral as a summation, as a weighted sum, as we did for the importance sampling and everything else. And this guy here is the distribution where we want to base our inference. This will not be known in closed form. So the question is, can we just plug in an approximation into the sequential Monte Carlo procedure, which we think will improve the efficiency of our Monte Carlo, the whole Monte Carlo procedure? And the answer is yes. We can use an approximation into the SMC procedure. It needs to be positive and unbiased, as it was proved in a different context here for Markov chain Monte Carlo, but it will work. And it will work. The proof that this will work is very simple. Let's just say that this distribution, sorry, one slide back. Let's say that I will approximate this guy here by this guy here for a specific sample theta. So instead of trying to solve this integral here using all the samples you have from the posterior, what I'll do is just choose just one sample from the posterior, and then approximate this guy here through this guy here, where theta will be theta k, where k was the index I sampled from these guys here. So what I need to do is to show that what I will do is to once again extend the space, but in this context it's a different extension of the space. I'll extend the sampling space from RD, which was my E, with the space of the theta parameters, and I'll call this space y. So the target distribution, the distribution I'm targeting now is a distribution that's operating on y, which is the approximation for gamma multiplied by the prior or the posterior for theta. So this is now, this joint distribution now is the one that I'm targeting. So if I can design an SMC procedure targeting this guy here, I'm done. Because once again, it's easy to see that this guy here, if I integrate theta out, this guy here has the marginal I want. Okay? So if I can show that this procedure will work, I will show that I can use the weights from this procedure into my SMC solving the problem I want. So similarly, I define things on the varying on time the same way I did before. So the difference between pi and pi t is the fact that I'm conditioning on bt and not on b. Okay? And I can also define pi t tilde on the y space. Okay? So now I have something that's defined on the path space. So this is defined on the path space of y. And y is the space that I increased with the parameter. So if I define pi tilde as something like this, so gamma multiplied by the backward kernels that now are operating on y, I can write this down as something like this. So this is my approximation for gamma. This is the prior or posterior distribution. And this is the product of backward Markov kernels. So this I can think as a product of backward Markov kernels on z multiplied by the posterior distribution on theta. So if I do the math now, so sorry, just to move samples backwards in time, I can sample from the posterior distribution, use these samples, which I will, to sample z backwards on time. And the importance distribution is very easy to calculate. So it's again the product of the importance distribution at time 1 multiplied by the forward Markov kernels on the extended space, z and theta. And if I put it all together, I get something like this. So my weights for the sequential Monte Carlo are just the ratio of gammas and q's. You do this ugly math here, full of index, and you see that luckily this guy here, which is the density of the posterior distribution, cancels out on the numerator and on the denominator. Why this is important? Because if you think that I'm getting these samples for theta through MCMC, I will not be able to calculate this guy here in closed form. Okay? This guy may be hard to compute. So now I have a procedure that can tackle this kind of problem here. Let me just go back. This kind of problem, I want to calculate this kind of conditional expectation, but also taking into account the uncertainty you have in your parameter estimation. Okay, so let me just go forward again. And so now the truth. So what is the truth? So the truth is that calculating this risk contribution is very, very simple. You can easily write a simple line of code that will sample lots of z's, conditional parameter, you do all your tricks, and then you throw away 99% of your sample. So this is very easy to do, but it's very inefficient. So the hard part of this is to make it efficient, and that's the whole talk is about, right? So the question we need to ask now that we have devised a procedure based on this SMC method is to ask the question, is our SMC method more efficient than playing Monte Carlo with rejection sampling? And how do we measure it? So the way to measure will be through something that's called the variance reduction, which will be defined as this. So I'll take the ratio of the variance for the estimated row, the risk allocations, when I do simple Monte Carlo, with the variance of these estimates when I do the sequential Monte Carlo procedure, and I'll normalize this through the correct numbers. So what are the correct numbers? So for the sequential Monte Carlo procedure, I have T levels, capital T levels, and in each one of the capital T levels, I need to sample n SMC times. So for the Monte Carlo procedure, I need to sample MMC, where MMC is this ratio here. So if I sample NMC times, this divided by 1 of alpha, 1 minus alpha, will be the amount of samples I'll be allowed to use in my estimation. All the rest will be out of the space I want, so I'll throw them away. So this is the ratio I want to look at. So just to talk a bit before I finish about the two case studies I mentioned at the beginning. So first thing, I'll simulate some data. I'll compute the true expected shortfall allocation through a very large Monte Carlo scheme to be sure that I'm comparing with something that's correct. I'll repeat this calculation many, many times to be able to estimate, coming back here, to estimate the variance of the estimator, which is the thing I care about. And then I choose the parameters for my SMC algorithm, which is the forward kernel I did not say a word about, the backward kernel, which I did not say a word about either, the MCMC kernel, which is that kernel M that do some tricky things that I did not say much about, and the number of steps T that I will say something about very soon. Okay, so very first example. So let's think that this is an example about operational risk. So we have 5 different lines of business. We will assume that each one of this line of business is the loss in this line of business given by a log normal distribution with known but different parameters, just to make things a bit more, slightly more realistic. The dependence between these losses will be given by a Clayton copula with some parameter that I'll be changing and showing how things work. And for this example, I'll fix the number of capital T, the number of levels that I'll use in this sequential procedure as something like this. So the first thing will be, the first level will be 0, so unconstrained thing. Then 10%, so this is a very light constraint, up to 0.9, 0.95, 0.99995, etc., all the way up to crazy numbers at the end here. So this will be also my intermediate set. So I first estimate the quantiles at this level. So I'll have I'll use for my intermediate levels B, the estimate of the quantiles at these levels. So this I'll do beforehand. And these are the results. So this is a colorful picture, which I'll try to make sense of right now. So remember that I have 5 lines of business. So I want to calculate that expectation for each one of those lines of business. So let's say that the blue dots here are the marginals for I equals to 1. And the other one is for I equals to 5. And the green one is the sum of all the marginal contributions, which is the expected shortfall. So this will come as a gift at the end. So if I calculate all the other 5, I sum them up, and this is an estimate for the expected shortfall. So what happens here? If I look at the log in the basis 10 of the variance reduction here on the y-axis, if I'm trying to estimate something that's not constrained at all, the SMC procedure and the rejection sampling will behave quite similarly. So there will be no variance reduction. So for this is something I would say somehow expected. If the quantile is very low, up to here, let's say up to 0.8, what happens is that the sequential Monte Carlo procedure is less efficient than doing rejection sampling. Of course, because it's very simple to sample lots of data, throw them away, and what you're throwing away is not a lot. But when you start to go to extreme quantiles, like, for example, for this operational risk stuff, we're looking at 0.399. And we start to get some variance reduction of order 10 to the second. So it's 100 times less variance, or if you go to some more reasonable quantiles, something like 10 to the half, which is about 3 or 4. Okay? So this is the amount of variance reduction you can get for this kind of problem. So this is for one specific parameter of my copula. This is for a different parameter. Things do not change much. The behavior is always something like this. But keep in mind that this is 0.1, 2, 3, 4 nines and a 5. And this is something that you actually don't want to calculate. Okay? So the second case study that I'll show you, it's a slightly more high dimensional. I have something that's 23, that has 23 dimensions. This is something that I presented last year here. I presented this model here last year in the last research in options. So think that the first 9 components of this vector are losses from current year. The next 9 are from previous year losses, and the other ones are for large claims. So conditional on some unknown parameter, theta, all these guys will have this red and blue here will have log normal distributions, and the green ones will have some Pareto distribution. Okay, so all the variables will be coupled together with a Gaussian distribution with covariance matrix given by the regulator. And the missing ingredient here is the level B's. So for the level B's, I'll do something like this. So I'll start at 0. And for each level BT, I'll say that BT is the percentage of particles that are above the level. So I'll take at time t, the amount of particles, the empirical quantile at time t. Okay, so in other words, BT is the empirical quantile from this weighted sample here. And therefore, at algorithmic time t, the level BT will be an estimate of 1 minus P0 to the power t, because I'm doing this iteratively on time. Okay, so in our example, I chose B equals to 0.5, so I'm always looking at the 0.5 quantile. So if you do this, you'll only be able to estimate these guys here. So if you go close to 0.9, you'll not hit 0.9 exactly, 0.99 exactly, but you get close from above and from below. If you increase this number here, you can get as close to 0.99 as you want, for example, as I said here. So all this, the value at risk for all these quantiles here will be estimated on the fly. And so this is just a histogram of how I'm estimating these quantiles for all these intermediate levels. So this dashed red line here is showing the value of the quantiles for a large Monte Carlo scheme. So this is, I cannot see much of a bias on this estimate, so it seems like it's estimating the intermediate levels correctly. So, and this is the interesting plot. It's exactly as before, but with many more colors now. So same color scheme, green, red, and blue for old, new, and large. And here I have something that's slightly worse than I had before, but it's still, for a complicated problem, I was sufficiently happy with. So this I'm having something, for some of the components of my 23-dimensional vector, I'm having a variance reduction of order 3 or 4, and all the way to 0. Okay? It's not that bad, it's not that good, but yeah, I can still see some room for improvement in these kind of things. So just to conclude, this kind of quantity I was talking about can still be used for something that's more interesting, I think, than just calculating the risk allocation, but it can be used to construct risk parity portfolio, risk budgeting portfolios. So these are portfolios where each asset or asset class contributes equally to the portfolio risk. The SMC algorithm may seem messy, but it's not that hard to implement. So we don't need to compute the value at risk if we want to compute the expected shortfall allocation. This is something interesting. And the parameter uncertainty can also be handled. So this is what I had to tell you, but now, as Georgie allowed me, I have some advertisement to do. So if you fancy learning a bit more about this kind of sequential or even simpler Monte Carlo algorithms, this summer at EMAP, at the School of Applied Mathematics at FGV, Professor Pierre Delmoral from IMPA in France will be giving a course about this kind of stuff. So the course will run from late January to early March, so the whole February, with Mondays, Wednesdays, and Fridays afternoon, with a 1 week break for Carnival if you have an excuse, if you want an excuse to come back to Rio again. So this may work for you. From the 8th of January to the 22nd of January, myself, Yuri Saporito, and Eduardo Mendes will be teaching some preliminary materials at FGV. And this will be mandatory for students seeking credit. So if any of you guys want to attend this, you are also welcome. So everyone is welcome, free of charge. Wear trousers because you cannot wear shorts at FGV. Okay, so thank you very much, and that's it.